Hello friends, this is Jim with Science Talk. This is kind of going to be a bit of a lengthy video, but I want to discuss with you some hypotheses for the start to the Younger Dryas period. So before we explore the various hypotheses, let's first define what is meant by the Younger Dryas, and that's spelled D-R-Y-A-S. The Younger Dryas lasted from about 12,900 to 11,700 years before present. And it featured a return to glacial conditions which temporarily reversed the gradual climatic warming after the last glacial maximum. And this glacial maximum started receding around 20,000 years before present. It is named after what's called an indicator genus, the alpine tundra wildflower Dryas octopetala, basically 8 petals, as its leaves are occasionally abundant in the late glacial, often mineralogenic rich, like the lake sediments of Scandinavian lakes. Now, just as a little side note, Dryas octopetala, 8 petals. Many plant species, when you count the number of petals in their flowers, it is a Fibonacci number. And what's meant by a Fibonacci number? Well, there's a famous mathematical sequence called the Fibonacci Sequence. And basically what it is to find the next number in the sequence, you sum up the previous two numbers that are there. And the first two numbers are 1, followed by another 1, 1, 1. And so if you have the first two elements of 1, then 1. 1 plus 1 is 2. Then 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. And then 8 plus 5 is 13. 13 plus 8 is 21, and so on. And that's how that's how the Fibonacci sequence works. As I said, many plants, the number of petals on their flowers is a Fibonacci number. It's one of these numbers. This is kind of one of those interesting things of nature. So anyway, what are the 3 hypotheses that are being considered here? One is a cometary or asteroid impact. 2, the Earth moving through a cometary debris field causing worldwide fires. And 3, the shutdown of AMOC, the Atlantic Meridional Overturned Circulation. As I indicated in another video, I am preparing some videos discussing AMOC and what it means to climate. It's what has been found has been very significant in my view, and this has great ramifications and implications for human civilization in terms of what this means to the climate. So be on the lookout for these videos coming up in the future. So back to the Younger Dryas. Physical evidence of a sharp decline in temperature over most of the northern hemisphere discovered by geological research has been the key physical evidence found for the Younger Dryas. This temperature change occurred at the end of what earth scientists refer as the Pleistocene epoch and immediately before the current warmer Holocene epoch. In the social sciences, this time frame coincides with the final stages of the Upper Paleolithic. The Younger Dryas was the most recent and longest of several interruptions in the gradual warming of the Earth's climate since the severe last glacial maximum, which occurred about 27,000 to 24,000 years before present. The change was relatively sudden, taking place in decades, and it resulted in a decline of 2 to 6 degrees Celsius and advances of glaciers and drier conditions over much of the temperate northern hemisphere. It is thought to have been caused by a decline in the strength of the Atlantic Meridional overturning circulation, which transports warm water from the equator towards the North Pole, in turn thought to have been caused by an influx of fresh, cold water from North America to the Atlantic. Let's pause right here, and this is a preview of what's coming in my future video that I alluded to. The Atlantic Meridional overturned circulation basically takes place where the Gulf Stream ends in the northern Atlantic. There, the Gulf Stream, which is fast moving, is warm, it's salty water, it gives off its heat, which is a reason why Scandinavia and the British Isles have milder climates than probably what they should have for the latitude they are located at. But it gives off its heat, so now this warm, salty water becomes cold, salty water, and it sinks. It sinks vertically through the water column, and then there's a return flow south at depth, some 1,000 meters down or so. And this is what's called the start of the worldwide conveyor belt. And it flows south to the North Atlantic, the South Atlantic. A branch splits off to the Pacific, a branch splits off to the Indian Ocean. But there's also, as it's flowing south, it's getting gradually warmer through the friction with other water masses, so it becomes less dense, it starts to rise, it brings up nutrients with it, and we have the Antarctic divergence zone, where this water upwells, it brings lots of nutrients to the phytoplankton, and the ecosystem just is off and running. It's called the Southern Ocean. The Southern Ocean around Antarctica is the most productive open ocean system on the planet. And we see the huge baleen whales, we see lots of krill, seals, fish, and so forth. Well, as recent studies have shown that this sinking, this overturned circulation, is slowing down. Slowing down due to all the glacial melt from Greenland. You're adding fresh water to the surface. It could be slowing down. If you shut down the conveyor belt, you shut down the major heat transport mechanism for the planet. I am one of those oceanographers that is of the opinion that global warming will bring on an ice age eventually because of this. I said, I will discuss this in greater detail in upcoming video. This is an extremely important topic, and I'm going to be covering it. Look for several videos. So I mentioned the three hypotheses for the start to the Younger Dryas period. The first is the cometary or asteroid impact. So let's look at that one. The classical view of the Younger Dryas cooling interlude has been that a surge of meltwater from the North American ice sheet was behind it. According to this hypothesis/theory, a large quantity of fresh water accumulated behind an ice dam, and the dam suddenly ruptured and dumped all this water into the Atlantic Ocean. The sudden influx is thought to have shut down the ocean currents that move tropical water northward, resulting in the cold, dry climate of the Younger Dryas. Some other studies suggested a major impact event. Perhaps a comet or asteroid was the catalyst. So that brings us to hypothesis number 2. According to an international team of scientists reporting in the Proceedings of the National Academy of Sciences, an asteroid or comet that landed in what is now the Canadian province of Quebec might have led to a significant climate change event known as Younger Dryas. This event took place about 12,900 years before present, which coincides with the start of the Younger Dryas period, and marks an abrupt global change to a colder, drier climate with obviously effects on flora, fauna, and humans. In North America, the big animals, mastodons, camels, giant ground sloths, saber-toothed cats, vanished. Their human hunters, known to archaeologists as the Clovis people, basically stopped hunting. They stopped because there were no more animals to be found, and they turned to more of a hunter-gatherer subsistence diet of roots, berries, and smaller game. The Younger Dryas cooling is a very intriguing event that impacted human history in a profound manner, Environmental stresses may also have caused Natufians in the Near East to settle down for the first time and pursue agriculture, explains study co-author Professor Mukul Sharma from Dartmouth College. Professor Sharma and his colleagues have discovered evidence supporting the theory of extraterrestrial impact. The team focuses on spherules, which are droplets of solidified molten rock that is expelled by the impact. The spherules in question were recovered from younger Dryas boundary layers at sites in Pennsylvania and New Jersey, the layers having been deposited at the beginning of the period. Basically, when you have an impact, sometimes you have a fusion of the material that can be part of what's called the ejecta, material that is ejected out of the impact crater site itself. So they go on to state that the geochemistry and mineralogy profile of the spherules are identical to rock found in southern Quebec, where the scientists, this team, says the impact took place. What is exciting in our paper is that we have for the first time narrowed down the region where Younger Dryas impact did take place, even though we had not yet found its crater, Professor Sharma said. There is a known impact crater in Quebec, a 4-kilometer wide colossal crater. However, based on mineralogical and geochemical studies, it is not the impact source for the material found in Pennsylvania and New Jersey. Professor Sharma continues to state that it may well have taken multiple concurrent impacts to bring about the extensive environmental changes of the Younger Dryas. However, to date, no impact craters have been found, and our research will continue to look for that. The third hypothesis, third hypothesis. Comet debris set off climate change. Did a blitz by comet bring up this change bring on the Younger Dryas? The evidence says researchers have found evidence of widespread and devastating forest fires around half the world, a blaze that was sufficient to block the sun, and this occurred at a geological boundary called the Younger Dryas, right? We're discussing that, and this is about 13,500 years before present or so. The evidence, they say, supports the hypothesis that planet Earth moved through a cloud of cometary dust, stones, and other material, and basically a lot of impacts occurred, and the impacts were enough to set fire to accumulated forest timber, peat, grasses across the Americas, Europe, and Western Asia. The conflagration triggered dramatic climate change and may have contributed not just to the decline of the mammoth and the mastodon and other large ice age mammals, but may have ended the Clovis civilization, which takes its name from the discovery of distinctive spear points in Clovis, New Mexico, of early North America. The evidence is reported in 2 papers in the Journal of Geology, which catalog vast quantities of soot and ash, all of the same timeline, which is preserved in ice cores, ancient glaciers, lake beds, ocean muds, rock sediments. So scientists can look at a number of places, and I just listed several of them, where we can find evidence of fire, evidence of deposition. We can even look at the isotopes, and looking at the isotopic signatures, we can then tell what the conditions were like in the atmosphere and so on. Scientists have also found evidence of ammonium, nitrate, acetate, oxalate, and other aerosols linked to the combustion of plant material. The link between the fires across the whole hemisphere and cometary impact comes from separate finds at the same horizon of melt glass, microscopic diamonds, platinum dust, and other debris that is basically explained from an extraterrestrial source. The big impact theory of mass extinction is now almost 40 years old. In 1980, U.S. researchers found a telltale concentration of the element iridium, which is very rare on Earth, but it's often found in asteroids and comets at the boundary of the Cretaceous and the Tertiary period 65 million years ago, commonly called the KT boundary, and linked a giant impact to the end of the dinosaurs. The study to which they refer refers to the father and son team of Luis Alvarez, who has since passed away, but his son continues the work. They were the ones that found the iridium layer in Gubbio, Italy. And the iridium layer was very thin, was very pronounced, and they dated right basically to the KT boundary. And then we found the impact crater was found off the Yucatan Peninsula in Mexico. So the idea of collisions from big rocks tumbling out of the skies has been basically well documented. This impact at the end of the Cretaceous is now widely accepted, though paleontologists may still argue about what might have actually killed the dinosaurs, but we now know that this impact did occur. For years, researchers have tried to match the extinction of Ice Age megafauna, woolly mammoths, North America, large marsupials in Australia, etc., with either climate change or the arrival of human hunters, or some agency from outer space, or some combination thereof. Now, researchers think the discovery of smoke in ancient ice cores and other places might indicate a quote-unquote smoking gun. The biomass burning was extensive and voluminous. We have evidence over North America, South America, Western Europe, and the western part of Asia that have blocked out the sun, causing an impact winter with profound effects of life on Earth, particularly large animals and humans. This is a statement from James Kennett, a professor emeritus at the University of California, Santa Barbara. The impact winter itself was also part of what triggered the younger Dryas cooling in the northern hemisphere. Arguments of this kind are closely linked to concern with climate change. So now we can look at what happened in the past and then extrapolate related to current conditions and what was going on. As I mentioned at the outset, the slowdown in the overturned circulation can lead to a cooling condition. Well, researchers have measured a slowdown in this overturned circulation. So we can often tell what could be in store for us by looking at what's happened in the past. And this is what scientists do. They say, oh, we have evidence that of these things. This is most likely what it led to. This is most likely what happened. We're now seeing similar condition. So we can predict with some statistical probability that this might be in store for us coming down in years and decades. So, again, relating to climate change here, we were doing what? We're burning fossil fuels. And we're basically increasing the temperature of the planet, okay? And this could be potentially very calamitous for humans. Planet Earth will keep going. It's what we're doing to ourselves. To make sense of what's happening now, as I just said, climate scientists have for decades been carefully analyzing climate change in the past. None of it linked to human action, but most of it linked to carbon dioxide levels in the atmosphere. Okay? We have a direct correlation. Increased levels of CO2, temperatures go up. Decreased CO2, temperatures go down. It's a direct correlation, and there's no denying that direct correlation and causation. Okay? It's well-established science. To do this, scientists have carefully reconstructed climate history from evidence in rocks, ice cores, marine sediments, lake beds, looking at and the ice cores are looking at the isotopes of carbon and oxygen and so on, and then try to identify the agents of change in the past. Cometary impact theory has its supporters, and asteroids and comets have been adding to Earth's minerals throughout Earth's history, 4.5 billion years ago. But paleontologists and climate scientists continue to argue about the disappearance of the great Ice Age species, about the role of human hunter-gatherers in any mass extinction, and about the levels of damage any cosmic collision may have caused. There is some thinking that humans hunted the large mammals to extinction. Some evidence for that. But like everything else, it's probably a combination of factors, not just one thing only. For example, if I have a pile of data and I want to fit a regression line to it, I can say, all right, let's pick one independent variable, and we'll run the regression line against that, and we might have an R-squared value of, say, 0.77. R-squared value is a measure by which we use to see how well the data points fit the predicted line. And the values range from 0 to 1. 0 basically meaning it's a pretty crappy fit. In fact, there is no relation. A value of 1 means that every single data point falls exactly precisely on the line. Well, that's if someone shows a regression line with all the points on the line, and I'm going to say that's fudge data. Okay, that does not happen. Okay, but so when we run regressions, we like to get an R-squared value of about 0.85 to feel any comfort in citing that. So let's say I run a regression with one independent variable and I get 0.77. Okay, not great, might be something there. But let's say now I add a second independent variable, and then I rerun my regression analysis. And now let's say my R-squared is 0.97. Well, that's a damn good model. And then we can say, okay, these two variables, these two independent variables explain the great majority of the variation in the data that we see. So when, one of the things I used to teach my statistics students is like, okay, construct the confidence interval around the mean, a 95% confidence interval. And then I'll say interpret your result. The students typically say, I can say with 95% confidence. A better way of saying is that 95% of the data falls in between in this interval. If I construct a 99% confidence interval, 99% of the data falls in this interval. That helps you get an idea of what the data is doing and what the range is. So if you have if two variables can explain 97% of the variation, that's an extremely excellent model. And then we say, okay, so obviously it wasn't just one factor that explained the response. We have two factors that explain the response. So trying to say, oh, it's either overhunting, it's either a lake dam busting loose, or it's either cometary debris being the only explanation, might simply be a combination of all those factors. So the latest studies add to the body of evidence. They tell a story of a fire that's vast and widespread. It consumed almost 1/10 of the planet's biomass over an area of 10 million square kilometers in a matter of weeks. The ice cores are the most persuasive because they're so well dated, said Professor Kennett. What's more, he continues, they provide sound geochemical results that point to a large biomass burning event precisely coinciding with the younger Dryas boundary layer formed when this major comet impacted Earth. So we have two hypotheses supporting this event being caused by some sort of cometary action. Thus, this gives scientists something to compare when looking at volcanic activities and or disruption to the Atlantic Meridional overturned circulation. So this is very interesting. Again, looking to what happened in the past, we can get hints, we can get clues compared to similar conditions currently at present to get an idea of what might be happening in the future. So it isn't just made up stuff. It is based on sound science, sound analyses that we then say, okay, this is what might be happening. And as it turns out, a lot of the models and predictions that, say, climate scientists have made have proven to be extremely conservative and actual an underestimation. But scientists tend to hedge our bets. We don't want to make overreaching statements. We like to keep it on the conservative side. And then if you get new data that when you reanalyze it and you then get new information that adds to our previous knowledge, then we can make adjustments to our predictions. That's how science works. That's what we're doing here. And the whole point when you create a model, like let's use my example of a regression model. Okay, I have this line, that the best fit line through my data points. Now I can sit there and say, okay, what can I expect to be my response in my dependent variable if I input whatever values for my independent variable or variables? What can I expect for my response to be? And that's the whole point of modeling. We take the data and we want to create some sort of, basically it's a mathematical equation to ascertain what future responses might be. Now with climate model, of course, it's extremely complicated and it takes a lot of supercomputing powers and so forth, but it's the same idea. You input your independent variables and you see what the output is, and then you model that. And in the case of climate, we look to what happens in the past, and then we try to make judgments as to what might happen in the future. So think of this video as kind of a warm-up to what's coming when I discuss the Atlantic Meridional overturned circulation videos. I hope you liked this video. If you did, please share this video. Please subscribe. Hit the bell when you subscribe so that you get notifications of when a new video is made available. I hope you'll consider supporting my work by becoming a patron at patreon.com/Science Talk with Jim Massa. Each of the words are separated by an underscore. If you're already a patron, thank you for your continued support. It is through word of mouth, for you sharing with your friends and your colleagues and co-workers and so forth, that this channel grows, because the information I share I consider to be important, and it has to be shared, it has to get out there so that people know what's going on. Thank you for your support. We'll talk soon.